presenter, Dr. Chris Bridges from the Surrey Space Centre. He's going to give us an update on the work going on at the centre and a report on the DeOrbitSail satellite.
Thank you,
Chris.
Right, so it's a pleasure to be back here again on such a wonderful summer morning. And today, really, the key thing that I'm going to give you an update for is one of our latest missions called DeOrbitSail. Now, as with most of my presentations that I give, I have the great opportunity to be able to give these sort of talks and talk to you all about the missions in a sort of top sort of level way. But I also am allowed to just really sort of mention some of the key people involved with this. We have Chiara, project manager, Richard, software, Martin, mechanical. There are lots and lots of people that are involved in building, designing, and operating spacecraft. And there's obviously lots and lots of partners that have contributed as well to the mission, either in hardware, software, and other things. All these things, they take a lot of time and a lot of effort. So I really just kind of wanted to give you a bit of a history as to where DeOrbitSail kind of comes from. And so DeOrbitSail is what we call an FP7 contract. It's a research proposal that we would have done with the FP7 European Commission. And as such, you tend to have principal investigators, project managers, and systems engineers. But you can kind of see from some of these dates, it's been going on really since about 2011. So March 2011 is really when we started on this. And it sort of kicked off to really investigate a whole swathe of things, including how we would go about using a 3U platform to do 3-axis attitude determination and control, but also how we would then deploy large solar sails. And so for those of you that perhaps don't necessarily know about these things, there have been other sails that have been launched before. For instance, there's been NanoSail D, there's also been LightSail, all of these sort of things that have been going up. But we have numerous PhD theses and other pieces of research on there to try and help maximise really how we can create drag sail type of objects. Okay, so as we all know, orbital debris is becoming a problem, or is certainly becoming a problem for those of us that want to perhaps build and operate sort of satellites from a more sort of lower baseline than perhaps some of our larger partners might have. But with that in mind, how do we go about doing that? A lot of these ones, they tend to deorbit out of control, and so we need to figure out what we can do about that. So there's only one that I'm aware of that is still attitude stable, and that's Icarus from JAXA. Okay? So we've got quite a way to go. There's been these missions from NASA, JAXA, Bill Nye, the science guy, and now us. And this one has been up in orbit now for a few weeks. So the consortium itself has a number of players. Unsurprisingly, Astrium, both the Surreys, DLR have been working on some of the boom assemblies and sail assemblies, ISIS with the radio, Caltech with some software. There's been lots of people involved in the project, and it's really just to hammer home how much effort it needs to sort of build it. And what you can see here is essentially sort of the configuration after the sort of solar panels have deployed. And in the centre down here, we've got our main bus, and then we'll have the sail itself, and then typically we'll have then the booms. And we'll talk about those in just a second. But before we kind of get onto that, I kind of wanted to get onto the mission objectives first. So at top level, we want to be able to demonstrate drag deorbiting of a nanosatellite, preferably with a few caveats associated with that. First one, can we do that with a maximum approximate area of about 16 square meters? Now in our case, that's a 4 by 4 meter sail. So if you imagine this CubeSat that's kind of this big, it's quite a large sort of area that we need to unfurl. As such, that's quite a lot of moments of inertia. Think of the actual inertia that's going to be associated with deploying that sail and then trying to keep it sort of head-on in your velocity vector, whilst at the same time travelling at best part of 8 kilometres per second. Okay? Quite a difficult task. The next thing is we want to make sure that we can stabilise that so we are always perpendicular. So if we're travelling in sort of a velocity direction, we want to make sure that is always on. And any sort of tip that we have in that tends to want to flip it, cause it to go out of control. Now there are some restorative forces with the way that the lift and drag equations work. They're essentially the same equation to some degree. And they do kind of restore, but there are certain points in that where they have resonances with the actual orbital frequency, as well as resonances between where you are in the sun's solar cycle. So there are certain altitudes where all of a sudden there's a potential loss of stabilisation. So we kind of want to check those as well. And the last one is see if we can do it from 650 to its demise being the operative word, there in about 3 months. So let's get on to the sexy stuff. Well, what I would call the sexy stuff. as I've just talked about earlier, we have got a bottom part of the bus. So this is a photo that we took in the clean room. Ooh, when did I take this? I think perhaps in March. Yeah, about March. Let's say March, maybe February. Which actually has the main sort of bus system here. And what you can actually see is, it's a bit faint here, but we've got some camera systems, we've got the harnessing around here, but it is essentially your computer, your power system, your comms board, as well as any control circuitry that we need to then operate this sort of large top block here. And what you can see here is you can see the stowed configuration of the sail itself. So when they put the sail in, it actually is very, very easy to get it out, as you'll see in a bit, but putting it back in can take us days. We actually had one guy, a guy called Nasir Adeli. He spent best part of 4 years trying to figure out how to best fold the sail and put it back into this tiny object. So we've got a 10 by 10 centimetre piece of material in there to try and maximise what we could get in there. The top part of here is the boom itself, and they're essentially on small rollers, and they are motorised and mechanically come out as and when we would like them to do that. But the actual sort of finished project kind of looks like this, where we've got the solar panels here on the sides, and they would eventually sort of come out. So then the key thing that we've been working on, sort of where I've been involved, is more towards the sort of end part. The researchers, all the developers, they've been doing all of the real sort of pieces, and really I'm just here to help get the message out of what DeOrbitSail is, what it can do, but more importantly show you perhaps just some of the things that we get up to and continue to get up to year on year. And so you can kind of see here the solar panels coming out. This is Martin. Martin's our mechanical engineer, and he's essentially pulling out these booms. Now, the reason why we have to pull them out is that everything's optimized for doing it in 0G. They're not used to doing them under the forces that we would typically see here on Earth. And instead of just keep picking it up and trying each motor around the other way, we kind of have this huge sort of mechanism. We're actually, I'm not sure if you can see it, yeah, just about. We've got these sort of faint sort of fishing line pieces to hold things up. So as soon as we wanted to sort of test those deployments and test the sail moving around, we can actually then do that in one of our labs. And you can then see, then this is the boom. It has the attachments to the sail. So this was the sort of period where we were testing everything from the ground station. And what it looks like when it comes out is it looks like this. This is the CubeSat, this tiny small piece in the middle, and then the rest of it is essentially a massive parachute. Okay. In this particular case, we kind of classify those as two key payloads. One is the actual sail itself, and the other is then the boom deployer. So the sail itself, obviously that needs to be stowed and configured in a certain configuration, as well as being able to make sure that it's supported then by the sail booms themselves. So in our case, we want to make sure that the spacecraft can have a maximal frontal area, but at the same time we want to make sure that it can be extended. The motorised booms deploy. As they extend, they will just unfurl it as it comes out. Now, the best thing to do that is to show you a video. So hopefully this will work. Yes. So this is my evening last night, just taking about 8 gigs of data, crunching it down to 30 seconds. You can kind of see here, this is one of our big lab areas. This is, in fact, where an old SSTL facility the Space Centre has taken over that we've now turned into a pseudo lab. It's not a clean environment in this particular one, but this is really just for doing the system end-to-end tests. So you can kind of see now how it kind of unfurls and comes out, and people checking it as it comes. Now, you can see this process here, when I'm looping this to about 31 seconds, it looks pretty damn quick. The whole process actually takes around 200-ish seconds, or should do when the sail is deployed. But this is just to give you a flavour as to sort of what's happened. They want to make sure that it doesn't get tangled when it comes out. If it gets tangled when it comes out, you know, the deorbiting will still work, but we want to actually maintain that attitude control, okay, when it comes out. If they don't actually come out and stay head-on, you're essentially halving your area on orbit average. So the next thing that was left to do after that was to do the integration with the PSLV. This is Chiara. Chiara's our project manager. Right at the moment, she's back over in the Space Centre. Hopefully be talking with DeOrbitSail this morning, and this is her taking it sort of out there. It's ready to go in its pod, and at the same time, then it will then go onto the rocket itself. You won't be able to see it because there's these other massive spacecraft from someone in the way. Apologies, Martin, if he's here. But DeOrbitSail is essentially a small cavity around the back here. Again, it's too small to see. Obviously, there's the large DMC spacecraft that are in here, but there's all sorts of small little pieces, but we're just behind the back here, which is obviously, you can see, such a minimal sort of piece on these sort of large missions. Okay, so let's get on to perhaps something a bit more interesting. Really what we wanted to do with DeOrbitSail is automate as much of it as we can. We have the full functionality of the AOCS system that we have with Stellenbosch and the team there. And really we wanted to sort of come out, deploy our antennas automatically, have a beacon activation at the right appropriate time, get ground contact, start our detumbling, deploy our panels, stabilize, deploy. Okay? And then burn in the atmosphere. I've been told to emphasize the word burn. So that being said, you can see it's actually not a real sort of large and long mission. This is really to test those deorbiting pieces, which are going to soon become very, very important, certainly with regards to sort of launching things in the UK. Testing of these technologies, having these deployed from a UK asset is something that's we really need to test. So the first sort of contact on the day really was done by Ken over in Oregon. And he was the first one to actually send us some full packets. And then moments later, we were getting then contacts from Japan, from Mike, from all sorts of other people, telling us that we had full battery, all of the currents were great, 21 dB signal, and thank you very much for keeping sending those in. This is more towards the beginning of the night, where everyone was looking actually vaguely okay. Again, this is sort of our SSC ground station operations, but we will be able to get sort of clear beacons every 15 seconds. So every 15 seconds we essentially go around and we will transmit then a new telemetry beacon that then people can pick up and pick down. They vary anything from about 2 bytes to about 36 bytes at 1K2 BPSK from the ISIS TRX UV. So what have we got kind of from that? The first thing that we've been looking at is obviously our power. So let me just talk a little bit about how we've changed our ground station. The ground station that we have that you've probably seen either the Bring Your Own Boards Day or from when I've last talked has actually significantly changed. We almost don't use any analog equipment anymore. I say almost. Okay, we still have an icon that we use to upconvert from about 100 milliwatts out of a software-defined radio transmitter, and we also use HPAs still and LNAs and these sort of pieces. But everything else we digitize as quick as we can. One of the things that we do is we have a couple of different ways that we do things. We go through either USRP, which is a well, not inexpensive. It's a couple of grand for a software-defined radio that has a couple of inputs, a couple of outputs, and it allows you then to play everything fully in the digital domain with a field programmable gate array. After that, we can plug it through something called GNU Radio, which is an open source platform for building and developing communications. We use that for mobile phone networks. We use it for large satellite missions. It's been used all over the world already, certainly for spacecraft missions. But also, we actually pipe that into something a bit more standard with the UZ7HO sound modem systems as well, to be able to do upper sideband demodulation, these sort of things. After that has gone through, we essentially will be putting that straight into a database and then beginning to plot it. But what's really, really great is you guys keep sending us these files, our KISS files, and this is just fantastic. We can easily get double the amount of our data when we do this. And we either run this through C or Python decoders, and again, Richard has been working really hard about integrating all these systems together so we can generate all of these sort of plots to see what we look like. So apart from sort of a minor blip, the battery has actually been super, super stable. And what we've been doing more recently is turning on and beginning to commission all of our ADCS systems. So one of the things that you would have noticed if you've been picking up DeOrbitSail is that every 15 seconds you typically get some sort of telemetry system, and actually what we've been doing is adding sort of new values into that chain. So we've got now the power systems, there's the radio pieces, there's the onboard computer sort of standard pieces, but then we've been adding things like your attitude determination, rate estimations, and magnetometry readings. So we want to be able to get those down as well. So we actually activated that. All of the powers look good. 140 milliamps was actually perfect for what we should have got from out of the lab. And so this is the setting up of the Cubane and the CubeSense sort of images, so we can start to estimate our rates. Just to give you, I guess, a brief update on where we're kind of going from here. One of the things that we have been doing, we've actually been doing quite a lot of uplink and downlink. We've started Dtumbly. as well, so we've been activating those algorithms. We've been changing the beacon to include those pieces of telemetry. AMSAT-UK have got the whole spreadsheet of all of our telemetry, all on the website, and if some of it is confusing, do let me know afterwards, and I can talk to you about specifics if parts of it doesn't make sense. So at the moment, we've been commissioning these pieces, and we've done 3 short 5-minute Dtumbly manoeuvres, but we want to know a bit more about what is actually going on in that part. So there will be further beacon changes to follow, and then after that, it's deploy panels, stabilise, sail, and then burn into our atmosphere. So this is kind of really a sort of short update, and I'm kind of expecting sort of questions as well. And so we've got the downlink, our uplink, they're all really operational. I think the last time I checked with the team, they were getting about 30 commands in per pass, going in really, really well, with new beacons being added to our 15-second sort of window. After that, I can't stress it enough, AMSAT's continued and continues to be and support us, and it's essential in our university-led missions where I don't have a ground station at Svalbard or all the way around the world. Because without you guys, it's really, I've been told again, with extreme thanks from the DeOrbitSail team that we continue to do that. People of note, well, usual suspects. I'm certain some of them are here. And if you have any KISS data or recordings, do send them. We've got just a Gmail account. Just to give you a bit of an update, I spoke to them last night. They will be testing the MEMS rate sensors as well, so we've got some other sensors actually on that particular system. These are new ones, and we want to check that our rates are what we think they are for our detumbling manoeuvres. And actually, hopefully, I might have already, I'll find out a bit later, actually might have moved our reaction wheels. So we'll see what's going on with the operations and how far they've got today. But we will then start to accelerate these ADCS operations kind of as we go. And that is a sort of brief update that I wanted to do in about 15, 16 minutes with time for questions. So with that note, I'd like to thank you for listening.
You say you're at 650 kilometers circa. What's your altitude?
Good question. I don't actually know the altitude off by heart myself. The altitude, sorry. So I've been
about 650.
Yeah, about that.
How does the solar radiation pressure and drag force compare at that altitude?
Oh, well, they kind of don't really. Solar radiation pressure, this is home turf now. So solar radiation pressure at different parts of the solar cycle causes our atmosphere to essentially swell. So with a high sort of solar output, whether it be from coronal mass ejections, solar flares, any geomagnetic activity at all, it essentially impacts the Earth and it essentially heats everything up, causes more interactivity. So our atmosphere starts to swell. The best way to think of it, the analogy that I teach with my students, is think of it more like an ocean. So you've got this nice calm state where it's a bit low, and as soon as you have any sort of geomagnetic solar activity, things start to swell up and you get lots and lots of waves. The solar, on average, the force and the acceleration you'd feel doesn't actually become the same until about 1,200, 1,300 kilometers. And the actual force, just due to the atmospheric density, is going to be orders of magnitude more than the actual solar radiation pressure. Icarus is at really, really high. I mean, it wouldn't be able to continue doing what it does if it was anywhere near the atmosphere.
Okay, any more? Question at the back?
Thanks, Chris. We had a question yesterday about why are all these sails metallized, because that really makes communication quite difficult.
Well, actually, yeah, so it...
We didn't know the answer to that. I mean, I think if you're actually sailing, and you want to, that's probably okay, but why, that's a reason for metallizing it. But if you're just using it to drag, I can't see why they're metallized.
So the reason why they are metallized is they typically come from sort of standard materials. So if we wanted sort of a transparent one, cost goes up. If you wanted one that's a bit more specific, I mean, when you buy those sort of materials, they sort of come as they are, and the actual tensilier strength that you need out the sail typically only comes from stuff that is metal. So to have something that's so thin that you can then pack into such a small space doesn't necessarily have the strength from regular plastics. They tend to break, or they tend to kind of stick, so when you fold them out, they don't always come out, whereas with something more malleable, even something like tinfoil, you know you can get that pretty damn flat if you're going to give it just a bit of tautness. The other part from that is that it is highly specular as well, so for the solar radiation missions, that is perfect. Yeah.
Chris, will we be able to see this from the ground when the sun angle is right?
Yes. So we actually, I hope, I've been in contact with a NASA astronaut who came and visited us about a month or so ago from DARPA. She now works at DARPA. What's her name? God, this is embarrassing. Well, I've been talking with her, and there's also a team out in at JPL as well. We do actually have a camera on the system as well, so we want to take a picture as we can sort of before the sail, and hopefully we'll get a shot looking just along the sail itself, he says. Yeah. Okay, hope. Okay, treat this with a pinch of salt. So we'll hopefully have a sort of before and after shot, and we need to do that before September. So if we don't do that before September, then actually the lighting conditions and the season would mean that we won't have that opportunity to do it again. So we want to be able to do these things fairly promptly. We don't want to hang around because we actually need to pay insurance on the spacecraft for every year that it is up in orbit. So if it comes down quicker, my premium goes down.
Yes.
Chris, with respect to altitude and drag,
Mm-hmm.
have you had any observations about the actual spacecraft's altitude and drag effects?
Yeah.
That surface area?
Well, so we haven't deployed any of the sail yet, but what we do know is that we believe it's around 4 to 8 degrees. So we have in our main long axis, we have a good spin of about 8 degrees, and the other two axes, they're like 0.1. So actually, you can, if the telemetry that's out there, in fact, there's plenty of stuff on. In fact, Mike's sort of sat blog, lots of KISS files sort of around, and we're looking to figure out how we're going to publish them on the SSC website as well, like I do with Strand.
Yeah, just one question.
Mm-hmm.
How many times do you calculate for after deployment and burning up?
How many times do we?
Between the two, deploy the sail and burning up.
Well, it depends on our start epoch and what the sun's doing. It'll absolutely come down in 120 days, but it's very, very hard to predict those things. The sun continues to be annoying.
Non-predictable.
Yeah.
Okay, any further questions? Yes, Jim.
Are you able to say a little bit more about the mechanism you use for Dtumbly?
The mechanism, yeah, absolutely. So what we use is magnetorquers combined with both MEMS magnetometry. In fact, one of the things I can show you that I didn't highlight perhaps quite as well, if I just go back in my slides, is this guy down here. So what we actually have down here is a small pedestal that has a magnetometer on it. So one of the things that we found, certainly with Strand 1 and other spacecraft, if you keep your magnetometer sort of tight within your bus, all of the loop currents that you're going to get with your solar panels, any sort of EMC that you're going to get out of the spacecraft, we just need to have a magnetometry reading as far as we can. And in the EC pod, there's a nice sort of gap in there. I'm looking at Wouter explicitly. But there's actually a small room there that we actually then have there. But inside there, we've then got another magnetometer, another MEMS one. Now, what we do with that magnetometry data is we align that with a particular field. So there's an actual model for the Earth's magnetic field. And from that, we can then work purely in what we call the B field. Okay, so if you can align things and you know roughly where you are, you can then begin to figure out how you can then dampen yourself with respect to those things. So you kind of get an X, Y, Z in your field, and that gives you an idea of perhaps where you are and what your attitude would actually be looking like with that model. You get kind of a couple of solutions, but one is obvious. From that, it is then just a zero finder. So you can use various different controllers to control one of your axes to zero, or to control one of it to be in a certain spin rate. So if you pick one from there, then it can allow you to then spin up on the other ones. So there is a coupling between those, but it's actually very, very standard. So if you wanted to look this up and Google this, you're looking for a B dot controller. So your B is your B field, dot is your derivative over time, and from that you can then control everything you need to, without going into any maths.
Okay, is there one final question? No further questions. I'd like to thank Chris for a very informative presentation.